Section 7.3, Law of Cosines. So we're solving triangles that are not right triangles. We talked about Law of Sines, now we have Law of Cosines. We're going to use the Law of Cosines if we know two sides and the included angle, that is, a side-angle-side triangle. Or if we only know all of the sides, so a side-side-side triangle. This is the Law of Cosines. Now, recognize your pattern real quick. The odd side out is the angle inside of the cosine function. A squared is equal to b squared plus c squared minus 2bc times cosine A. So recognize that all the sides on this side of the equation are the ones that are not on the other side, and this side is opposite this angle. Once you notice that, all of these end up being that exact same pattern. So then let's use it. We want to solve triangle ABC if side A is 4, if side B is 3, and side C is 6. First off, what kind of triangle is this? Well, notice that this is a side-side-side triangle. That is the information that's given. So at this point, we just need to find one of our angles. So if I want to find angle A, I've just chosen that one. It doesn't really matter. Then remember that the law of cosines is a squared is equal to b squared plus c squared minus 2bc times the cosine of this angle opposite that odd man out over there. So cosine of angle A. Well then, what happens? I just plug in everything I have. 4 squared is equal to 3 squared plus 6 squared minus 2 times 3 times 6 times cosine of unknown angle A. At this point, we just need to solve for cosine of A. So 4 squared is 16, 9 plus 36 minus 6 times 6 is 36, cosine of A. 9 and 36 is 45, so I'm going to subtract 45. Subtract 45. I get negative 29 is equal to negative 36, cosine of side A. Divide by negative 36. Divide by negative 36. I get that 29 36 is equal to cosine of A. At this point, I need to take the inverse cosine of both sides. And I have good news. Recall that cosine inverse actually has a range of between 0 and pi, which means that we don't have to be concerned about multiple triangles occurring when we take the inverse cosine. And so that's really a nice thing, because we know that whatever we get here for A will be the correct answer for A. And so A is equal to cosine inverse of 29 over 36. If we have to approximate, we'll round to 2 decimal places. And I get that rounded to 2 decimal places, this is approximately 36.34 degrees. Well then, if I want to find angle B, we can use law of cosines again if we so desire. And so, A, I now have, is approximately 36.34 degrees. Then let's use law of cosines to find angle B. So, that's going to be b squared is equal to a squared plus c squared minus 2ac times cosine of b. Watch out for that c times cosine. And so then, this is side b, which is 3 squared, is equal to 4 squared plus 6 squared minus 2 times 4 times 6 times cosine of b. Then I get 9 is equal to 16 plus 36 minus 48 cosine of b. I then get 16 and 36 added is 52, so I'm going to subtract 52. Subtract 52. I get negative 43 is equal to negative 48 cosine of b. So divide by negative 48. Divide by negative 48. I get that cosine of b is equal to 43/48. Now I'm going to take the cosine inverse of both sides, which gives me that b is equal to 26.3 26.38 degrees. 26.38 degrees. At this point, of course that's approximation, at this point recall that if we wanted to find C, C is just going to be equal to 180 degrees minus, and since I've approximated it's an approximation, 36.34 degrees minus 26.38 degrees minus 26.38 degrees. Sorry about that strange order of writing it. So I get that angle C is 117.28 degrees. So now let's solve triangle ABC. If side length A is 2, side length B is 3, angle C is 30 degrees. At this point, recognize that we need to find the side opposite C. So we're going to use law of cosines, because what kind of triangle is this? This is a side angle side triangle. And so law of cosines is going to give us that C squared is equal to A squared plus B squared minus 2AB times cosine of C. C is what we're looking for, so C squared is equal to 2 squared plus 3 squared minus 2 times 3 times cosine of angle C, which is 30 degrees. This one we could actually find the exact value, but we'll still approximate most of these unless they ask specifically for an exact answer. So this is then C squared is equal to 4 plus 9 minus 12 cosine of 30 degrees. I'm not going to round until the end if I can help it. And so C squared is then equal to 13 minus 12 cosine of 30 degrees. Then I can take the square root of both sides. Now, of course, taking the square root of a square, you may need to consider plus and minus, but I claim that because we're talking about a real-life triangle that makes sense in terms of our two dimensions here, it's going to have to be a positive answer. And so we're only going to be a positive, and so I claim that C is then approximately 1.61. And so side length C is approximately 1.61. At this point, if you so desired, now that we have side C opposite angle C, you could actually use law of sines to find angle B or angle A. Either of these will work perfectly fine now. And so let's actually do that. Sine of angle C, 30 degrees, divided by 1.61 is equal to, and let's just find angle A. So that's going to be sine of angle A divided by side length of A, which is 2. Multiply both sides by 2. So then I have 2 sine of 30 degrees divided by 1.61 is equal to sine of A. But then, of course, I need to take sine inverse of both sides. So sine inverse, I get that A is equal to sine inverse of 2 times sine of 30 degrees divided by 1.61. And so then I get that angle A is approximately 38.397, which rounded 2 decimal places becomes 0.40. So 38.40 degrees. Now, of course, this is an approximation. And so then if I want to find angle B, I claim that angle B is, of course, going to be approximately 180 degrees minus side length C, which is 30 degrees, minus this 38.40 degrees, which is then approximately 111.6 degrees. 111.6 degrees. And so recognize that these are approximations because we rounded originally. And the moment that you round, you create error, and there could be some situations where we're a little bit off, but that's what we're working with. And so if we really wanted to get this closer to exact, we would need to use the C that we found earlier, which was the square root of 13 minus 12 cosine of 30 degrees. And so just recognize that if you're building a bridge, you want to be more exact, whereas if we're just solving these triangles for the sake of practice, we understand the law of cosines, and we can use the law of sines after that. We're good to go. So some application problems. A golfer hits an errant tee shot that lands in the rough. A marker in the center of the fairway is 160 yards from the center of the green. While standing on the marker and facing the green, the golfer turns 125 degrees towards his ball. He then paces off 35 yards to his ball. How far is the ball from the center of the green? Okay, lucky for us, we have this nice picture here already for us, which means that at this point the only thing that we need to find is this side over here. Whatever we wanted to label it, I've decided to label that opposite 125 degrees side as C. Regardless, that means that C squared is equal to 160 squared plus 35 squared minus 2 times 160 times 35 times cosine of angle 125 degrees. And so once we do this calculation, take the square root, we have found our solution. If you so desire, you could take the square root right now and type all of this into your calculator, and we could just get our approximation all at once. And I get that this is approximately 182.34 yards. Alright, real quick, let's run through which laws we use for each specific situation. So let's say that we're told A is equal to 14, B is equal to 23, C is equal to 10. So let's identify what type of triangle we have here. Well, recognize that we have a side-side-side triangle. Because we have a side-side-side triangle, we're going to start with what? Well, we're going to at least start with the law of cosines. If we have A is equal to 207, that's side length A. And if it helps you to label your triangle for the moment, that's fine. A is 207. Angle B is 43.8 degrees. And angle C is 57.6 degrees. 57.6 degrees. Notice that we have an angle-side-angle triangle. Angle, side, angle. Alright, so what do we do with an angle-side-angle? Well, angle-side-angle triangle is solved by law of sines. Alright, next one. Let's say that we have angle A is equal to 112 degrees. Angle C is equal to 37 degrees. And side length A is equal to 84.7. Well, recognize that we have an angle-angle-side triangle. Okay, angle-angle-side triangle. That's going to be solved by which one? Law of sines. Alright, for the next one, we're given that angle B is equal to 101 degrees. Side length A is equal to 960 degrees. And side length C is equal to 1042. Sorry if I called A degrees. It's a side length, not in degrees. So then, what do we have? We have a side angle side, side angle side. Side angle side, what are we going to use? We're going to use law of cosines. Alright, for E here, what do we have? We're told that side length B is equal to 17.26. Side length A is equal to 27.29. And we get angle A is equal to 39 degrees. And so for this one, I think we want to call it side-side angle. Side-side angle. And remember that side-side angle is law of sines. Also remember that side-side angle triangles are the one where we could have one solution set, two solution sets, or it's possible that we get no solutions from this situation. F is A is equal to 61 degrees, B is equal to 39 degrees, C is equal to 80 degrees, and so we have angles, angles, angles. So A is equal to 61 degrees, B is equal to 39 degrees, C is equal to 80 degrees. Alright, so what do we use to solve this one? Well, if you recall from your notes, we actually never addressed this situation. And the reason we never addressed this situation is because triangles with fixed angle ratios if you don't have side lengths given in any way, shape, or form, I actually do not have any knowledge of how this triangle scales. Because when I say scale, it could be massive, or it could be super, super tiny, and it could vary everywhere in between. And so the truth is that right now, we don't have enough information for this, and so this one's going to be neither is used, because as of right now, it has no solution. We don't actually have a way to solve this triangle, because without any ratio size, that is a side length to help us understand how big the triangle is, triangles with these angle measurements could be of any size. One more example just for some interesting practice. Let's say that two airplanes leave an airport at the same time. The first flies 240 miles per hour in a direction of 290 degrees. The second flies 210 miles per hour in a direction of 330 degrees. After 1.5 hours, how far are the planes apart? Okay, this one I just threw in so that we could use a little bit extra information and try to extrapolate and do some problem solving. And so, because we have this superimposed on an xy coordinate plane, that is specifically they're telling us what direction these airplanes are flying, well, it says that the first one is flying in a direction of 290 degrees. Well, where does 290 degrees live? 290 degrees lives in quadrant 4, a little bit counterclockwise of the negative x-axis. And so that's our negative 290 degree rotation. Sorry, positive 290 degree rotation. And then let's look at the other airplane. Well, the other airplane, it rotates a 330 degree rotation, and so that's going to be a little bit shy of the positive x-axis, and so that's going to be our 330 degree rotation. Well, what's really interesting here is that at this point I claim that we can find the important thing, which is actually what the angle is between these two rays. Well, specifically I know that that blue ray that I have here is 330 degrees. The other one is 290. Well, what's 330 minus 290? 330 minus 290 means that the angle between their directional paths is only 40 degrees. Okay, so that's super useful. Well, now we have a little bit more extrapolation. We've got these two airplanes flying, and so specifically the one that's going in the 290 degree direction, it flies 240 miles per hour. Remember, they're both flying 1.5 hours, so if I'm trying to figure out the distance, what do I need to do? I just need to multiply the speed times the time. So 240 miles per hour times 1.5 hours, because that's an hour and a half, that's going to give me 360 miles. And so this plane that's flying in the 290 degree direction goes a distance of 360 miles. Then for the other airplane, the one that's going in the direction of 330 degrees, it's flying at a rate of 210 miles per hour. And since it also flies for an hour and a half, multiply 1.5 times that time, 1.5 times that speed, and so it gets a distance of 315 miles from the airport. 315 miles from the airport. Alright, at this point, notice that now what we want to find is the distance between the two airplanes. And so if I want to find this distance, I'll call it C for now, then notice that I have an angle measurement trapped between two known side lengths, then I can find the opposite side length. And so in terms of law of cosines, that's going to be C squared is equal to 360 squared plus 315 squared minus 2 times 360 times 315 times cosine of 40 degrees. And then if we want, we can go ahead and take care of that square root and find it all at once. C is then going to be equal to the square root of 360 squared plus 315 squared minus 2 times 360 times 315 times the cosine of 40 degrees. Make sure you're in degree mode. And I get that this is approximately 234.7 miles. And so that's how far apart I claim those two airplanes are after an hour and a half.